Hi, peeps. I'm going to go through this video with y'all, and I know when I do my young kids, my algebra kids, I go pretty slow and try to be patient. I don't want it to be boring for you, so I'm going to try to go through this fairly quickly. Feel free to pause, rewind, and then if you have any specific questions, write them down, circle them, and we'll go over it in Zoom. Okay, I've just done these review problems for you if you're interested. It's just, I don't want to lose the stuff we did from first semester. So I've given you the answers. I'm going to go forward. You can ask questions about it tomorrow or in the Zoom if you want. Okay, this first part is just talking about some of the vocab that you read in 5.1. I'm not going to go over it. I think you guys have seen it and talked about it. If you have questions on any of that, come back and let me know. The one thing I will note is that is common notation to represent the sample space. So just be aware of that. All right, what kind of number is probability? And I feel silly having to say it, but it's between 0 and 1. And the reason why I have to say it is I get people who give me answers, and we'll play with probability throughout in some form of or another, but I get people who give me answers to probability problems that are like 4.3. And calculator said 4.3, but you got to look back and make sure you're looking at the e to the negative whatever, which is talking about your exponent, scientific notation, moving the decimal. So just be aware of your answers and make sure you give me answers that make sense. Obviously, closer to 0 means that event is less likely. Closer to 1 means it's more likely. In the middle means we're equally likely. I don't know, lame rule. It's got to add up to 1. I shouldn't say that's a lame rule. It's actually kind of a common question, and I'll show you what I mean. It's one of the last problems in this example, but you know the total of everything that can happen, the total probability of everything that could possibly happen, all the events, has got to be 1. This is just a notational thing. You don't see it a ton, but I want to show it to you in case you did see it, and it's just talking about the complement of A or the probability that event A does not occur. We're going to run into problems down the road where I'm going to ask you to find a probability, and actually finding that probability is harder than finding the probability that it doesn't happen. So a lot of times when we want to talk about the probability of A, it's going to be easier to do the complement of A and then 1 minus that will give you A. So 1 minus the probability of A not occurring is going to be the same as A occurring. And all I'm saying is there are times when calculating that is easier than going to calculate that. Okay, this is notation you got to know. That U stands for union, and it means or. That upside down U, or I like to call it an N, stands for and. Ooh, look, there's an end in and it means intersection. There's an N in intersection as well. And our general basic definition for 5.1 is if you're doing an or, you can just add the two probabilities. If you're doing an and, you can just multiply the two probabilities. However, both of those have conditions based on their appropriateness. And we'll fix this in our next slides, in 5.2. But in order to use this ghetto rule for or, you have to have disjoint or mutually exclusive events. Disjoint and mutually exclusive are synonyms. You'll hear and see both of them, so you got to know both words. But all it means is that your two events cannot happen at the same time. And a lot of times one of the tools we'll play with are Venn diagrams. If this is event A and that's event B, those two events are disjoint because there is no overlap. These two events, let's say C and D, are not disjoint. They are not mutually exclusive. Therefore, I could not use this rule for that type of problem. So if A and B can happen, you are not just allowed to add A plus B, and I'll show you what that means here in the next example. Well, and this is hard. I mean, I understand it, but I understand the frustration. But you guys hear disjoint / mutually exclusive, and then you hear independent, and you have a real hard time separating those two situations. And independent events mean that the fact that A has happened does not change the fact that B happens. In other words, one event has no influence over the other. It will not change the probability of the other event. And that is not the same as disjoint or mutually exclusive. I'll get into independence more in 5.2, but that's kind of our basic general ghetto rule. And there are times when that works. There's nothing wrong with it. And problems are literally that easy. Just add those together or just multiply them. And yet there are other problems where I don't get to use that. And yet we're going to put that multiple choice answer on there, and it's tricky. Okay, this is just talking about sample space, and I'm going to skip B. B is kind of stupid because how are we measuring time? Days, weeks, months? And then also there's no end to it, so I don't want to deal with that. But let's do JoJo. JoJo, he comes to class each day. He's either tardy or he's on time. So the sample space for that event, for that situation, is either tardy or on time. He's saying that they come to class each day. Those are the only two options that it could be. So there's only two events in that sample space. Another important piece to this is, are those events equally likely? The reason why I say that is, if I were talking about flipping a coin, your sample space would be a head or a tail. I'm flipping one coin. And those events are equally likely. So that's why we say the probability of getting heads is 1 out of the two total options, 1/2. Well, are these equally likely? Does he have a 1/2 shot at being on time and a 1/2 shot at being tardy? And I would say they are not equally likely, which means now I got to be careful. I can't just talk about how many things are in the sample space. I would have to have probabilities associated with them as well in order to do any calculations. Rock never say die, shoots 2 free throws. This one's an important one because it gets you. And you guys will usually say, he hits it and hits it. He made them both. He hits it and misses it, meaning he made one of them. And then you'll say he misses both of them. Miss and miss. But the reality is, we missed an option, and this becomes a very important option that causes us problems down the road. Hit and miss is different than miss and hit. It is a separate option. Even though the result ends up being the same, because there's two ways to make one shot, that's going to increase the likelihood that he only makes one. Back to the concept of, are they equally likely? Depends. Is Rock a 50% free throw shooter? If he is, then those events are equally likely. If he isn't, they are not equally likely. And it's just something you got to think about. All right. So this next piece, and I get a little overboard with this, is dealing with counting how many events there are in a sample space. And if your events are equally likely, knowing the number of possibilities in the sample space will generally be your denominator. So in this situation, when I'm tossing 2 coins, that is absolutely no different than Rock shooting 2 free throws. There are 4 options in the sample space because there are 2 things that can happen on his first coin. There are 2 things that can happen on his second coin, and we just multiply those in order to get our 4 total possibilities. And again, because a coin is fair, 50-50, all 4 of those options would be the same. Therefore, you know your denominator to the probability problem that we'll ask you down the road will be 4. Well, what if I toss 3 coins? 2 things that can happen on the first one, 2 things that can happen on the second one, 2 things that can happen on the third one. That ends up being 8. Now, are some of those outcomes the same when you toss 3 coins? Yes, but because there are more than one way to do some of those things, their likelihood is higher. There are going to be times when, and I know this is painful right now, but you kind of get stuck and you're wondering, don't be afraid to go write all 8 of those things out. I could get heads, 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 tails, heads, tails, heads, tails, heads, heads, tails, 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 heads, tails, heads, tails, and heads, tails, tails. There are my 8 possible things that could happen, and they are all equally likely. The problem is when we go, which means the denominator will be 8. The problem is when we go to ask a question, when I ask all heads, knowing this number tells me my denominator is 8, and how often can I get all heads? Only one way. So that probability is 1/8. Well, what is the probability then that I get exactly 1 head? Well, I know the denominator is going to be 8. And now I got to go through and look at exactly 1 head? No. Exactly 1 head? No. Exactly 1 head? No. Exactly 1 head? Yes. Exactly 1 head? Yes. Exactly 1 head? Yes. Exactly 1 head? No. So all those are out. Those are the 3 that satisfy this statement. So that probability would be 3/8. So again, the point of this is if all of the outcomes are equally likely, knowing how many things can happen will determine your denominator. Okay, if I roll 2 die, there's 6 things that happen on one, 6 that can happen on the other. That is 36 total possibilities. Wait a second. How do you get 36? 6 times 6. But there's not really 36. You can get a 2, a 3, a 4, a 5. Sorry. You can get a sum of 2, a sum of 3, a sum of 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, but that's not all of the possible things that could happen. I could get a sum of 7 in 6 different ways, 7 different ways. 5 and a 2, a 2 and a 5, a 6 and a 1, a 1 and a 6, a 3 and a 4, a 4 and a 3. So I guess 6 different ways. So because there's more ways to get a 7 when you add them up, that's the most likely value when you roll 2 die. But there are still 36 possible outcomes. Roll 3 die, 6 times 6 times 6, 218. 218, 216. You can check me. Obviously, this is not something I would be able to write out. I ain't going to write out all 218 of those. But if your sample space is relatively small and you're stuck, sometimes that idea is pretty good. I'm going to skip the rest of these because it just starts to get a little bit. Actually, I'll do one of them for you. They're telling me repeats are okay versus repeats are not okay. That is important. Can you have the same letter or the same number on a license plate? I don't know. What are the rules? I'm going to say if they're okay, 3 digits, 10 times 10 times 10. I am saying 10 because there are 10 one-digit numbers, 0 through 9. And 3 letters, 26 times 26 times 26. Whatever that number is tells me how many possible license plates we could have. If you do that multiplication, I'm not going to waste our time with some huge number. Believe it or not, we had to change our license plates because we ran out of license plates in Nevada. They reformatted them a few years ago so that they could get some more license plates in there, which is pretty impressive. We had that many license plates in Nevada. I'm going to skip the rest of those. All right, first, real probability stuff we've done. They've done a survey, and they've told me that 63% of people said In-N-Out was their favorite, 12% said McDonald's, 14% said Wendy's. They left a question mark for Burger King. If those are the only options they gave me, What's the probability somebody would choose Burger King? Well, if those are your only options, you know it's got to add up to 1. So you're just going to do 1 minus 0.63 plus 0.12 plus 0.14. And again, I say 1 and I'm playing with decimals. You can convert from decimals to percents and back and forth. We don't care. If I ask for percent and you give me a decimal, that's fine. Fractions, decimals, and percents are all the same for us. You've got to be able to switch back and forth between all three. What's the probability that the person chooses Wendy's or, keyword, McDonald's? So notationally, we would write this: probability of Wendy's or Mickey D's. Because these are mutually exclusive or disjoint, that means nobody was allowed to choose a McDonald's and Wendy's. You had to pick one. And there is no overlap. There's no way one choice could satisfy two of these things. So I am able to use my ghetto addition rule, which is just probability of Wendy's plus probability of Mickey D's. Get used to writing this notation. It's going to be common. Wendy's was 0.14, Mickey D's was 0.12. We got a 0.26 or a 26% chance that a randomly selected person would say McDonald's or Wendy's. We've got a not in and out. So I could go add up McDonald's and Wendy's and Burger King, or I could just do 1 minus the probability of in and out. Which is 1 minus 0.63 or 0.27. If 2 randomly selected people are asked what their favorite fast food restaurant is, what is the probability that both would say in and out? So I need probability of in and out and in and out. Well, now I've got an and situation. And I have to ask myself, are these independent? This choice, is it independent of that choice? And my answer to you would be, it depends on what's going on. If I ask a couple walking down the street, those people are not random. They are related, and they are likely not independent. But if I really select 2 random people, they're not answering around each other. There's little things I can do to try to keep them independent. They should be independent events. Now, for the most part, we're going to tell you if they are independent or not, and you'll see as we go, which I didn't do here, which I should have, but that's because I want to talk about that concept. The fact that they said random people allows us to assume that their responses will be independent of one another. Well, that means I can use now in and, intersection versus or is the add, and is the multiply. So I'd go 0.63 times 0.63, and whatever that is, I think it's something like 37%. I can't remember. I'm not going to waste our time with calculator. You can do that. And then what's the probability neither would say in and out? So again, I could do 0.12 plus 0.14 plus whatever that was. I can't remember. 11? Yeah, something. I think it was 11%. I can't remember. I could add those up and then do that total times itself, because I would need both of them not to say in and out. So again, this is an and because it said both, or neither of them. Not in and out, and not in and out. Sorry for the shorthand notation. I'm just trying not to keep you on here forever. Which was was it 37? .37 times 0.37, and again, that would give you the probability that neither of them would say in and out. And again, I still would need this concept of 2 randomly selected people. Okay, I'm going to stop this video and just save it, but the next video I'm going to combine sections 2 and 3, just so you know, and it's probably more of the realistic stuff we're going to play with in chapter 5.